Welcome to an exploration of how tiny capsules and droplets behave completely differently from their larger counterparts due to their enormous surface-to-volume ratio. This is a nanocapsule, a tiny sphere with an outer shell and inner cargo. At this scale, the surface dominates everything that happens inside. Let's start by understanding what surface-to-volume ratio means and why it matters so much at small scales. The surface-to-volume ratio compares how much surface area an object has relative to its internal volume. Mathematically, we write this as S over V, which equals surface area divided by volume. For a sphere, which is the shape most capsules approximate, this ratio has a particularly simple form. The surface area of a sphere is 4 pi r squared. The volume of a sphere is 4/3 pi r cubed. When we divide surface area by volume, we get 3 over r. This is the key equation. The ratio increases as radius decreases. Here's a visual comparison. Smaller spheres have much larger surface-to-volume ratios. The tiny sphere has a ratio of 10, while the large one has only 2. Let's do some concrete calculations to see just how dramatic this difference becomes at the nanoscale. First, let's consider a macroscopic capsule with a radius of 1 millimeter, about the size of a small pill. That's 1 millimeter, or 10 to the minus 3 meters. The surface-to-volume ratio is 3 divided by 10 to the minus 3, giving us 3,000 per meter. Now let's consider a nanocapsule with radius 100 nanometers, which is typical for drug delivery systems. That's 100 nanometers, or 10 to the minus 7 meters. The surface-to-volume ratio is now 3 times 10 to the 7 per meter. That's 30 million per meter. The ratio has increased by a factor of 10,000. This means surface effects are 10,000 times more important in the nanocapsule. This bar chart dramatically shows the difference. The nanocapsule's surface-to-volume ratio towers over the macroscopic capsule's ratio. So why does this huge surface-to-volume ratio change everything? Because surface reactions now dominate the behavior. In large capsules, the release of contents is controlled by bulk diffusion through the interior volume. But in nanocapsules, the surface properties control everything: binding, unbinding, and transport across the membrane. Here we see drug molecules inside a nanocapsule. Most molecules are close to the surface and interact with binding sites on the membrane. Let's ask an important question. In a nanocapsule, what fraction of molecules are near the surface versus in the bulk interior? Consider a 100 nanometer radius nanocapsule with a 5 nanometer thick surface layer where molecules interact strongly with the membrane. The total volume is 4/3 pi times 100 cubed, about 4.19 million cubic nanometers. The bulk interior volume, excluding the surface layer, is 4/3 pi times 95 cubed, about 3.59 million cubic nanometers. The surface layer volume is the difference, about 600,000 cubic nanometers. That means 14% of all molecules are in the surface layer. In a macroscopic capsule, this would be less than 0.01%. Another critical effect is ligand mobility. Molecules on the curved surface can move and reorganize rapidly. Ligands are molecules attached to the capsule surface that help with targeting, stability, or controlled release. On highly curved surfaces like nanocapsules, ligands have more freedom to move laterally because of the geometric constraints. This animation shows ligands moving around the capsule surface. Their mobility allows them to cluster, reorganize, and respond to local conditions. The curvature itself creates mechanical stress in the membrane, affecting its properties. Curvature stress scales as 1 over r squared, so it increases dramatically as capsules get smaller. Now let's explore how diffusion itself changes inside these tiny, confined spaces. In bulk materials, diffusion follows Fick's law, where flux is proportional to the concentration gradient. Fick's first law states that flux J equals negative d times the concentration gradient dc dx. Fick's second law, for time-dependent diffusion, states that concentration change over time equals d times the second spatial derivative. But inside nanocapsules, molecules are so confined that they constantly interact with the walls, breaking the assumptions of Fick's law. Inside a nanocapsule, Molecules are constantly colliding with the walls and each other. Their paths are highly constrained compared to bulk diffusion. The effective diffusion coefficient inside the capsule can be 10 to 100 times smaller than in bulk solution. We write D effective equals D bulk times some function of confinement that accounts for the geometric restrictions. Let's answer another key question. How long does it take for a molecule to diffuse from the center to the edge of a nanocapsule? The characteristic diffusion time scales as r squared over d. For a 100 nanometer radius capsule with a typical diffusion coefficient of 10 to the minus 10 meters squared per second, the time is about 10 to the minus 4 seconds, or 0.1 milliseconds. That's incredibly fast. This means molecules equilibrate across the entire capsule almost instantly. Internal diffusion is not the rate-limiting step. Because surface effects dominate, the release kinetics from nanocapsules often look nothing like classical diffusion models predict. For large capsules, classical Fickian diffusion predicts that cumulative release grows with the square root of time. The mass released m of t is proportional to the square root of d times t. But nanocapsules show complex multi-phase release patterns, burst release, plateau phases, and delayed release. This graph compares classical bulk release, which follows a smooth square root curve, with nanocapsule release, which shows an initial burst, then a slow phase, then accelerated release. Why do we see this difference? 3 key mechanisms are at play. First, surface desorption. Molecules already near or on the surface are released immediately in a burst. Second, membrane permeability can change as cargo is depleted because membrane stress and structure depend on what's inside. Third, ligands on the surface reorganize dynamically, opening or closing pores and changing release rates over time. The release rate constant becomes a complex function of time, surface concentration, and membrane stress. Let's use an analogy to make this intuitive. Think of a nanocapsule like a tiny blister full of medicine. In a normal-sized blister, the skin is just a thin barrier. But in a nano blister, the skin is proportionally huge and dominates everything. In a large blister, the properties of the interior fluid, like viscosity and diffusion, determine how medicine spreads and releases. But in a nano blister, the skin's properties, like permeability, flexibility, and binding sites, dominate the release mechanism. The skin can stretch under internal pressure, develop tears, or reorganize its molecular structure to open or close pores. So medicine release depends far more on what the skin does than on simple diffusion through the interior fluid. These 3 factors, surface binding and unbinding, membrane stress and deformation, and pore dynamics are the skin properties that control nanocapsule behavior. Let's look at a practical application. Nanocapsules designed for targeted drug delivery in medicine. Here are typical parameters for a drug delivery nanocapsule used in cancer treatment. Radius between 50 and 200 nanometers. Membrane thickness around 5 to 10 nanometers. Drug loading typically 10 to 30% by mass. The design challenge is to control the release rate once the capsule is in the body, targeting tumor sites. Targeting ligands on the surface, recognize tumor cells. Once bound, the capsule must release its drug payload at the right rate. The dominance of surface effects creates opportunities for triggered release, using pH, temperature, or enzymes to change surface properties. For example, a pH drop in tumor tissue causes protonation of surface molecules, which opens pores and triggers drug release. You might ask, why not just use bigger capsules and avoid these complications? The answer is that only nanocapsules are small enough to penetrate through blood vessel walls, into tissue, and potentially into cells themselves. So surface dominance is both a challenge we must engineer around and an opportunity for sophisticated control mechanisms. Let's develop a quantitative model that captures surface-limited release kinetics. We assume that release is limited by desorption from the inner surface, not by diffusion through the bulk interior. The rate of mass release is negative K desorption times surface area A times surface concentration. Surface concentration is proportional to bulk concentration with a partition coefficient beta. Substituting, we get dm dt equals negative K desorption times 4 pi r squared over V times m times beta. For a spherical capsule, V equals 4/3 pi r cubed. Simplifying, we get dm dt equals negative 3k desorption beta over r times m. This gives exponential decay. M of t equals m0 times e to the negative 3k desorption beta over r times t. The key insight is that the release rate constant is inversely proportional to radius. Smaller capsules release faster. We can define an effective rate constant K effective equals 3k desorption beta over r. Compare a 100 nanometer nanocapsule to a 10 micrometer microcapsule. The nanocapsule releases 100 times faster because of its smaller radius, even with identical surface chemistry. This graph shows exponential decay for both sizes, but the nanocapsule releases its contents much faster due to its larger surface-to-volume ratio. Finally, let's examine curvature-driven stress, a purely geometric effect that becomes important at nanoscale. Curved membranes experience mechanical stress simply because they're curved. This is described by the Young-Laplace equation. The pressure difference across a curved interface is gamma times the sum of the two principal curvatures. For a sphere, this simplifies to delta P equals 2 gamma over r, where gamma is surface tension. This internal pressure increases dramatically as radius decreases, creating mechanical stress in the membrane. Let's calculate this for a water droplet to see how large the effect is. Water surface tension is about 0.07 newtons per meter. For a 100 nanometer radius droplet, the pressure difference is 1.4 megapascals, which is 14 atmospheres. That's enormous internal pressure. This stress can deform the membrane, change its permeability, or even rupture it under certain conditions. These arrows pointing inward represent the high pressure trying to compress the capsule contents due to surface tension. Curvature stress directly affects membrane properties like thickness, lipid packing, and protein insertion. Membrane permeability becomes a function of both pressure and curvature, adding another layer of complexity to release kinetics. Combined with ligand mobility and surface reactions, this creates highly dynamic membrane behavior that changes over time. Let's summarize why nanocapsules behave so differently from their larger counterparts. First, surface-to-volume ratio scales as 1 over r, making surface effects dominant at nanoscale. Surface reactions, not bulk properties, control almost every aspect of behavior. Ligand mobility and reorganization on curved surfaces create dynamic responses to environmental changes. Curvature-driven stress adds mechanical complexity that affects membrane structure and permeability. Release kinetics deviate strongly from simple Fickian diffusion, showing burst release, plateaus, and triggered behavior. Internal diffusion is extremely fast, so surface processes become the rate-limiting steps. In conclusion, nanocapsules are radically different from larger capsules due to the dominance of surface effects, high curvature-driven stress, and dynamic membrane behavior.